Tonight, you are going to die in the most extraordinary way any human being has ever imagined. You are going to fall into a black hole, and I am going to walk you through every single second of it. What you will see, what you will feel, what happens to your body, your mind, your sense of time, and eventually the very atoms you are made of. This is not a metaphor, and it is not a horror story. Everything you are about to experience is built from real physics. From the equations Einstein wrote more than a century ago, from the measurements of Nobel Prize-winning astronomers, and from the first actual photographs of black holes taken by telescopes the size of our entire planet. By the end of this journey, you will understand black holes more deeply than almost anyone you have ever met. Before we begin the descent, 3 quick things. If you are new here, subscribe to the channel right now because we make long, slow, deeply researched journeys through the universe. The kind you can put on at night, close your eyes, and let carry you somewhere else. Hit the like button because it genuinely tells the platform this journey is worth showing to other travelers. And drop a comment telling me where in the world you are watching from and what time it is there because I read every single one. And there is something I love about knowing this same story is playing in a bedroom in Manila, in a truck cab in Texas, in a kitchen in Lagos at 3 in the morning. Wherever you are, whatever time it is, stay with me until the end, because the ending of this story is not what you think it is. Now close your eyes if you want, take a breath, and let us begin the fall. You wake to the soft hum of a ship. The walls around you are smooth and pale, curved like the inside of an egg, lit by a gentle amber glow that comes from nowhere in particular. You are lying in a padded acceleration couch, and as your eyes adjust, you remember, piece by piece, how you came to be here. You volunteered. That is the strangest part. Out of 8 billion human beings, you raised your hand for the one mission no one returns from. The mission designers were honest with you from the first briefing. They told you that this journey has one direction. They told you that the data you transmit on the way down will teach humanity more about gravity, time, and the structure of reality than every laboratory on Earth combined. And they told you with a kind of gentleness you did not expect from physicists, that depending on which black hole you chose, your final hours could be either instantaneous oblivion or one of the most beautiful experiences a conscious mind has ever had. You chose the beautiful one. Your ship is called the Odysseus, and right now it is coasting through a region of space so remote that the nearest star is a faint point of light behind you, indistinguishable from the thousands of others scattered across the dark. Ahead of you, still invisible to the naked eye, is your destination, a supermassive black hole with a mass of 40 million suns. Not the largest in the universe, not even close, but large enough for what you need. Large enough that you will survive the crossing. Large enough that you will have time, real time, hours of it, to see what no living thing has ever seen. The ship knows the way. You unstrap from the couch and float to the observation deck, a hemisphere of flawless transparent diamond at the bow, and you look out into the black. Here is the first thing nobody tells you about approaching a black hole. For most of the journey, there is nothing to see. A black hole with no active accretion disk, a quiet one, a sleeping one like yours, emits no light at all. It is a hole in the universe in the most literal sense, a region that produces nothing, reflects nothing, and reveals itself only by what it does to the light of everything behind it. So you do what the mission planners trained you to do. You watch the stars, and after a few hours of coasting, you begin to notice it. There is a patch of sky ahead of you where the stars are wrong. They are not missing exactly. They are displaced, pushed outward from a central point, crowding around the edges of a growing circle of absolute darkness, like a congregation backing away from something at the center of a room. The black hole is bending their light. Every photon that passes near it gets its path curved by the warped space-time around the mass. And from your point of view, this makes the stars behind the black hole appear to slide away from it, smearing into arcs, doubling into mirrored pairs. You are looking at gravitational lensing with your own eyes, the same phenomenon that made Einstein famous in 1919, when a British expedition photographed stars near the eclipsed sun and found them shifted exactly as general relativity predicted. Except what those astronomers measured as a shift of less than 0.02 of a degree, You are watching swallow a quarter of the sky. The circle of darkness grows, and now you see the ring. As the hours pass and the Odysseus falls faster, pulled by a gravity that strengthens with every kilometer, a thin line of light appears around the edge of the darkness. Faint at first, then unmistakable. It is a perfect circle, silver and delicate, like the rim of a wine glass catching candlelight. This is the photon ring, and it is one of the strangest structures in the universe. At a distance of 1.5 times the radius of the event horizon, space-time is curved so severely that light itself can orbit the black hole in a circle. Photons from every star in the universe, arriving from every direction, can be captured into this orbit, loop around the black hole 1 time, 2 times, a dozen times, and then escape, flung outward toward your eyes. The ring you are seeing is made of light from everywhere. Somewhere in that thin silver circle are photons from the star you were born under. Somewhere in it are photons that left their galaxies before the Earth existed, wandered across the universe for billions of years, swung around this black hole like skaters around a rink, and are only now completing their journey by ending it in your retina. You are seeing the entire sky wrapped around a circle of nothing. The mission log chimes softly. You are now 100 million kilometers from the event horizon, roughly 2/3 of the distance from the Earth to the Sun, and you are falling at over 9,000 kilometers per second. On any other journey, this would be a terrifying speed, almost 3% of the speed of light, fast enough to cross the United States in half a second. Here, it is barely the beginning. The black hole does not care about your speed. It has been accelerating things like you for billions of years. Interstellar dust, wandering comets, the occasional doomed star. Everything that has ever crossed into its sphere of influence has been gathered up, sped up, and drawn down the same invisible slope you are on now. Gravity is not a force pulling on you, not really. That is the old way of thinking, the way Newton saw it, and it works well enough for planets and cannonballs. What Einstein understood is that mass curves space-time itself, and objects in freefall are simply following the straightest possible paths through that curved geometry. You are not being dragged. You are coasting downhill through a landscape whose shape was carved by 40 million suns worth of mass. And the remarkable thing, the thing you keep returning to as you float in the observation dome watching the dark circle grow, is that you feel nothing at all. You are weightless, serene. In freefall, gravity is undetectable, because every atom of you and every atom of the ship falls together at the same rate along the same path. Galileo discovered this by dropping weights. Einstein called it the happiest thought of his life, and you are now living inside it, plunging toward the most extreme object in the universe in absolute silent comfort. You eat a meal. You sleep briefly. When you return to the dome, the black hole has changed. The circle of darkness now spans half the sky, and the lensing has become surreal. The entire universe of stars behind you is being squeezed, from your point of view, into a shrinking ring of brilliance surrounding the black disk ahead. Light from stars that are physically behind your ship is being bent around the black hole and funneled forward into your view, so that ahead of you, wrapped around the darkness, you can see distorted images of what lies behind you. The geometry of the sky has stopped making ordinary sense. Ahead is behind. The universe is becoming a tunnel of light with darkness at the end of it, and you are falling down the middle. The ship chimes again, 10 million kilometers to the horizon, and here, at last, you cross the threshold the mission planners called the point of honesty. This is the distance at which, for your chosen black hole, no engine that humanity could ever build, no engine physics could ever permit, would be able to pull you back out. Escape would now require accelerating to more than the speed of light, and nothing that has mass can ever reach the speed of light, let alone exceed it. The universe has quietly closed the door behind you. Nothing marked the moment. No alarm sounded, no barrier appeared. No sensation touched your skin. You simply passed, at some unmarked point in the silent dark, from a traveler who could still turn around into a passenger who cannot. You knew this moment would come, and you thought you had made peace with it, but you find that your heart is beating hard anyway, an old animal rhythm sounding an alarm in a place where alarms mean nothing anymore. You breathe, you let it pass. You chose this. And the truth is that the door closed for you the moment you accepted the mission, back when the black hole was a slide in a briefing room. This is just the universe making it official. While the ship falls, let me tell you how your species came to know this thing exists at all, because the story of the idea is nearly as strange as the object. And you carry that whole story with you in the ship's library. The accumulated stubbornness of 2.5 centuries of people refusing to stop thinking about an impossible thought. It begins in 1783 in an English village with a clergyman named John Michel, a man so quietly brilliant that history nearly forgot him entirely. Michel knew Newton's laws, and he asked a simple question with an unacceptable answer. Light, he reasoned, must be affected by gravity like everything else, and everybody has an escape velocity. So what happens if a star is so large that its escape velocity exceeds the speed of light? His answer, written out in careful 18th century prose and read before the Royal Society, was that such a star would be invisible, that its light would rise, slow, and fall back like a thrown stone, and that the largest and most magnificent bodies in the universe might therefore be permanently dark, detectable only by the motion of luminous objects circling them. Sit with that for a second, because it is astonishing. A century before Einstein was born, a country parson predicted dark stars, and predicted that we would find them by watching visible stars orbit around nothing, which is exactly how astronomers confirmed the black hole at the center of our galaxy more than 200 years later. Michel was forgotten, his paper buried, the idea dismissed as a curiosity, and the dark star waited. It waited through the whole 19th century, and it stirred again in the winter of 1915, in the mud of the Eastern Front of the First World War, where a German artillery officer named Karl Schwarzschild, one of the finest astronomers of his generation, was serving his country by calculating shell trajectories. Einstein had just published the field equations of general relativity, 10 interlocking equations of such difficulty that Einstein himself doubted exact solutions would ever be found. Schwarzschild, in the trenches, in the intervals between bombardments, found one within weeks. He solved Einstein's equations exactly for the space-time around a single spherical mass, and inside his solution, unbidden, was a special radius, a distance from the center at which the mathematics did something alarming, where time as measured from outside froze and the geometry seemed to tear. He mailed his work to Einstein, who presented it to the Prussian Academy with admiration. And within months, Schwarzschild was dead, of a disease contracted at the front, never knowing that the radius bearing his name marks the boundary of the most extreme objects in the universe, never knowing that you tonight crossed a threshold that carries his signature. For decades afterward, the greatest physicists alive tried to kill the idea. Einstein himself published a paper in 1939 arguing that Schwarzschild's strange radius could never form in nature, that the universe would find a way to prevent such an absurdity. Arthur Eddington, the most celebrated astronomer of his era, declared that there should be a law of nature to stop a star from behaving so preposterously, and he said this while publicly humiliating the one young man who had done the mathematics showing. There was no such law. A 19-year-old Indian physicist named Subramanian Chandrasekhar, who on the boat voyage from Madras to England had calculated that a dying star's core above a certain mass could not be saved, that no known force could hold it up. That collapse was not an anomaly, but a destiny. Chandrasekhar was mocked in public session by Eddington. The field turned away from his result for a generation. And half a century later, he received the Nobel Prize for being right, because the universe does not consult authority. It simply proceeds. The same year Einstein tried to forbid black holes, 1939, a young American physicist named Robert Oppenheimer, together with his student Harlan Snyder, published the calculation that settled the matter for anyone willing to read it. They followed a collapsing star all the way down using Einstein's own equations, and they found in cold print everything you have lived tonight, that to a distant observer the collapse appears to slow and freeze at the critical radius, the star fading and reddening into a permanent ghost, and that to an observer writing the collapse, the crossing happens in finite, ordinary, uneventful time. Both stories in the same mathematics, both true, neither privileged. Oppenheimer then went off to lead the building of the atomic bomb and never worked on the subject again, and the collapsed star sat in the literature, unnamed and mostly unloved, for another generation. until the astronomers began, unwillingly, to find them. Because the universe, it turned out, had been shouting about black holes the entire time, at wavelengths nobody had learned to hear. In the 1960s, radio astronomers cataloging the sky found point sources of staggering power. And when the optical astronomers ran down their positions, they found what looked like faint blue stars. Except the light of these stars was shifted so far toward red that they had to be billions of light years away. And if they were that far away, then to appear as bright as they did, each one had to be outshining an entire galaxy of 100 billion suns from a region smaller than a solar system. They were named quasars, and for years they were simply a crisis because no known process could produce that much energy in that little space. Nuclear fusion, the mightiest furnace then known, converts less than 1% of matter into energy. The quasars demanded something far beyond it, and there is exactly one engine in the universe beyond it. Matter spiraling down into a supermassive black hole, shearing against itself in a whirlpool of plasma, friction heating it to millions of degrees until it blazes across the electromagnetic spectrum, converting mass to light with up to 40% efficiency, in a single feeding black hole, eating no more than a few suns worth of gas a year, will outshine its entire host galaxy. The impossible objects were the dark stars, announcing themselves by their table manners. You saw one on the way here. You will never forget it, and neither would anyone. Early in the voyage, the Odysseus passed within a few hundred light years of an active galactic nucleus, a feeding supermassive black hole, at a safe angle above the plane of its disk. And you spent an entire day at the dome, unable to look away. The accretion disk spread below the ship like a hurricane of fire the size of a solar system, banded in whites and golds and furious oranges, brightest at the inner edge where the plasma completes its final orbits at half the speed of light before vanishing over the horizon. The inner glow was so intense the ship's dome had to filter it a millionfold, and even then it lit your face like a sunrise. You watched the Doppler beaming with your own eyes, the side of the disk rotating toward you, blazing several times brighter than the receding side. The light of the approaching plasma compressed and intensified by its own velocity, an asymmetry no artist would dare paint, and every real photograph confirms. And from the poles of the thing, perpendicular to the disk, rose the jets. Twin spears of plasma, narrower than their length by a factor of thousands, launched by magnetic fields wound into helices by the black hole's spin, punching outward at very nearly the speed of light, and extending, the ship's instruments confirmed, for hundreds of thousands of light years far beyond the visible edge of the host galaxy. Rivers of matter and energy fired across intergalactic space by a single spinning engine, smaller than the orbit of Neptune. You understood, watching, why these objects regulate the growth of galaxies. Why the biggest galaxies in the universe stopped forming stars when their central engines ignited. Why astronomers speak of black holes and galaxies growing up together, each shaping the other across cosmic time. The mass of the central darkness tracking the mass of the surrounding stars in a tight correlation across every galaxy we have ever measured. The monster is not a parasite on the galaxy. It is a governor, a thermostat of cosmic fire. And the calm spiral of stars you were born inside was sculpted, in part, by the quiet giant at its center. Your own destination is silent because it is starving. Its neighborhood swept clean long ago, and that silence is the only reason your approach was survivable at all. A feeding black hole would have vaporized the Odysseus with radiation while you were still light years out. You are falling into the mouth of a sleeping predator, and the sleep is the mercy. Let me tell you about the object you are falling toward, because you have hours yet, and because understanding it will change what you see when you arrive. A black hole is what remains when gravity wins an argument it has been having with matter since the beginning of the universe. Every star that has ever burned is a battlefield between two forces. Gravity pulls every particle of the star inward, trying to crush it all into a single point. The energy released by nuclear fusion in the core pushes outward, holding the star inflated like a lantern. For millions or billions of years, the two forces balance, and the star shines. But fusion needs fuel, and fuel runs out. When a star at least 20 times more massive than our sun exhausts the hydrogen in its core, it begins burning heavier and heavier elements in an accelerating panic. Helium for hundreds of thousands of years, carbon for centuries, oxygen for months, silicon for about a week. Each stage buys less time than the last, and the final product of all this desperate burning is iron. Iron is the ash of the universe. It is the one element whose nucleus is so tightly bound that fusing it releases no energy at all. Fusing iron costs energy, so the moment a massive star develops an iron core, the fire at its center simply goes out. And gravity, which has waited patiently for 10 million years, collapses the core in about a quarter of a second. Think about that number. A sphere of iron more massive than our sun, roughly the size of the Earth, collapses to a ball 20 kilometers across in less time than it takes you to blink. The outer layers of the star, suddenly unsupported, come crashing down at a quarter of the speed of light, strike the rigid collapsed core, and rebound in an explosion called a supernova, an explosion so violent that for a few weeks a single dying star outshines the combined light of 100 billion others. Every element in your body heavier than helium was forged in stars, and much of it was scattered into space by exactly these explosions. The iron in your blood spent time in the core of a dying star. The calcium in your bones, the oxygen you are breathing right now inside the Odysseus, all of it is stellar ash, recycled through generations of stars and supernovae before it settled into a yellow dwarf star and its third planet, and eventually into you. But sometimes when the dying star is massive enough, the rebound fails at the center. The collapsed core is too heavy for even the strange quantum pressures of compressed neutrons to support, and it keeps falling, past the density of an atomic nucleus, past every threshold known physics can describe. The core falls out of the visible universe entirely, wrapping space-time around itself so tightly that a boundary forms, a surface of no return, and everything inside that boundary is causally severed from everything outside, forever. That is a stellar mass black hole, and the galaxy is full of them, perhaps 100 million in the Milky Way alone, almost all of them invisible, drifting between the stars. Your destination is something grander. The supermassive black holes that sit at the centers of galaxies were not born from single stars. They grew over billions of years by feeding. Gas, dust, entire stars, and other black holes, all swallowed and incorporated, generation after generation, until the largest of them accumulated the mass of billions of suns. The one you are falling toward holds 40 million solar masses, compressed inside an event horizon roughly 240 million kilometers across, wider than the orbit of Mars. And here is a fact that almost nobody believes when they first hear it. Because the size of the event horizon grows in direct proportion to the mass, but the volume inside grows much faster, the average density inside a supermassive black hole is astonishingly low. Yours has an average interior density lower than the air you breathe on Earth. If you could fill the orbit of Mars with ordinary air, you would have built something with roughly the gravitational credentials of the monster ahead of you. Black holes are not dense in the way people imagine, not the big ones. Their power is not in being packed tight. Their power is in the totality of the mass and the absoluteness of the boundary. The mission log chimes, 1 million kilometers to the horizon. You look up and you find that the black hole is no longer a thing in the sky. It is the sky. The darkness fills everything ahead of you, everything to the sides. A floor of perfect black extending in all directions like a midnight ocean seen from a falling plane, and the entire luminous universe. Every star and galaxy that exists has been compressed by the lensing into a circle of light directly above and behind you, shrinking, brightening, blue shifting as your speed climbs. You are now falling at more than a third of the speed of light. The light of the universe overhead is turning strange colors as you catch up to it, red stars turning gold, gold stars turning white and blue, and dim stars brightening as their light piles up against your onrushing eyes. The physicists have a term for what the universe is becoming above you. They call it the escape window, and over the next hour you will watch it change in ways no simulation ever fully prepared you for. But first, you have an appointment. Because at this distance from the black hole, falling along this trajectory, you are about to cross the photon sphere, the region where light itself orbits, and the mission planners told you that the view from inside it would be worth the entire journey. They were right. As the Odysseus falls through 1.5 times the radius of the horizon, the geometry of light around you performs its final magic trick. At this radius, remember, photons can circle the black hole forever, which means that here, and only here, light can travel from the back of your own head, orbit the entire black hole, and arrive at your eyes from the front. You look ahead into the darkness, and in the thin, luminous band at the edge of the shadow, you see your own ship. The Odysseus, faint and smeared and unmistakable, its amber running lights traced into a ghostly arc, an image of yourself painted in orbiting light. You are looking at the back of your own ship by light that has lapped the abyss. You raise a hand, and a heartbeat later, deep in that silver ring, something impossibly far away and impossibly close raises one too. No one has ever waved at themselves across the curvature of space-time before. You spend a long moment doing it, laughing alone in the dome, delighted in a way you had not expected to feel this deep into a one-way journey. And it occurs to you that this is a thing the universe has been capable of for 13.8 billion years, this mirror made of gravity. And it has been waiting all that time for someone to fall past with eyes and a sense of humor. The moment passes. The ring drifts overhead as you fall through it. Below the photon sphere now, there are no more circular orbits of any kind. Not for light, not for matter. Everything at this depth spirals inward. The region you have entered is a one-way current, and the horizon is close. You check the ship clock and you do something the mission planners asked you to do at exactly this point in the descent. You look at the transmission log, at the record of the data stream the Odysseus has been sending home since the journey began, and you think about what is happening to those signals. Because what is happening to them is one of the strangest and most beautiful facts about the place you are about to enter. Every radio pulse your ship sends outward has to climb out of the gravitational well you're falling into. And climbing costs the light energy. Not speed, light always moves at the same speed, but energy, which for light means frequency, which means the signals arrive home-stretched, lowered, reddened. As you have fallen deeper, Mission Control has watched your transmissions redden and slow. The pulses you send every second are arriving further and further apart. Your voice in the data stream has been dropping in pitch, your words lengthening, like a recording played at ever slower speed. And this is not a technical malfunction. This is time itself differing between you and them. Deep in a gravitational well, time genuinely runs slower relative to the outside universe. Not seems to run slower. Run slower. Clocks at different heights tick at different rates in this universe, and the difference has been measured on Earth between clocks separated by a single meter of altitude, and it is corrected for every second in the satellites above the planet you were born on, whose navigation systems would drift by kilometers per day if their engineers ignored what Einstein wrote in 1915. What is a nanosecond correction in Earth orbit becomes, here, an abyss between you and everyone you have ever known. From Mission Control's point of view, your descent has been slowing for hours. The closer you fall toward the horizon, the slower your clock ticks relative to theirs. And as you approach the boundary itself, the ratio grows without limit. They will watch your final transmissions stretch from seconds apart to minutes apart to years apart. Your last clear image, the last photograph of your face in the dome, will arrive frame by frozen frame across their decades. To them, you will never quite reach the horizon. You will hover at its edge, reddening, dimming, slowing, an eternal photograph of a falling traveler, growing fainter until the stretched light of you is too feeble for any telescope to gather, and you fade from the universe like a note held past hearing. They will never see you cross. From the outside, no one ever crosses. The universe outside keeps a version of you pinned to the threshold forever. A ghost stitched into the last layer of escaping light. That is what they see. It is not what you experience. And there is no contradiction in this. No paradox to resolve, because relativity's deepest lesson is that there is no single master clock in the universe. No privileged observer whose account is the true one. Your reference frame and theirs simply tell different stories, and both stories are correct. In theirs, you freeze at the boundary and fade. In yours, this happens. There is something else you should know about the object below you, a secret in its anatomy, and it concerns spin. The black hole you chose is a slow rotator, nearly ideal, selected by the mission planners for the simplicity of its geometry. But almost every black hole in the universe spins, and spins ferociously, because black holes inherit the rotation of everything that ever fell into them. A collapsing stellar core is like a spinning skater pulling in her arms, and when the core of a star shrinks by a factor of 10,000, even a lazy stellar rotation is amplified into something monstrous, remnants spinning hundreds of times per second at birth. And the supermassive holes, fattened for billions of years on disks of orbiting gas that all turn the same way, are wound up like the springs of cosmic watches, some of them measured spinning at better than 9/10 of the maximum rate that physics permits. And a spinning black hole is a genuinely different animal, described by a different solution of Einstein's equations, found in 1963 by a New Zealand mathematician named Roy Kerr, who accomplished what half a century of physicists had failed to do and solve relativity exactly for a rotating mass. A result so consequential that Chandrasekhar himself called the discovery the most shattering experience of his scientific life. Around a Kerr black hole, the space-time itself is dragged into rotation. This is not a metaphor. The phenomenon is called frame dragging, and it means that near a spinning mass, space is a current, a moving medium swept around the hole like water around a drain, and it has been directly measured, delicately, by satellites in orbit around our own gently spinning Earth. Close to a rapidly spinning black hole, the dragging becomes absolute, and there exists a region outside the event horizon, a flattened zone called the ergosphere, within which no force in the universe can hold you still. Inside the ergosphere, you may still escape. The horizon is below you yet, but you cannot refuse to orbit. Hover on the mightiest engines imaginable, thrust against the current with the energy of galaxies, and you will circle the hole anyway, carried by space itself, because within that boundary, standing still would require moving backwards through the local flow faster than light. The universe permits you to leave. It does not permit you to be motionless. And the ergosphere holds a treasure, discovered on paper by Roger Penrose in 1969. Because the drag space within it moves with such energy, an object that dives into the ergosphere splits in two and throws one piece against the rotation on precisely the right trajectory, can fling its other piece back out of the region, carrying more energy than the whole assembly brought in. The excess is stolen from the black hole's rotation. The hole spins imperceptibly slower, and the escaping fragment departs enriched, and the arithmetic is honest. Energy extracted from the one object in the universe that supposedly gives nothing back. A civilization advanced enough could orbit a spinning black hole and mine it, feeding it garbage and receiving power, running cities of 1 trillion souls on the slow unwinding of a dead star's rotation. And some physicists have speculated entirely seriously that the last civilizations of the far future, in the age after the stars burn out, will huddle around spinning black holes as their ancestors once huddled around fires, drawing down the final reserves of extractable energy in a darkening universe. The rotating interior is stranger still. Where your slow hole hides a point at its center, a spinning hole hides a ring, a circle of singularity, and the mathematics of Kerr's solution, followed with a straight face, permits trajectories that thread the ring and emerge into regions the equations can only describe as elsewhere, other spaces, other times, and it permits deep inside a second horizon, an inner boundary wherein falling travelers would watch the entire future history of the outside universe blue shift and pile up into a curtain of light of unbounded energy. Most physicists believe that this inner cascade of light, called mass inflation, slams the door, that the idealized tunnels of the Kerr geometry are destroyed in any real black hole by the very light falling in behind you, that the mathematics describes a perfect vacuum solution, which nature, messy and luminous, never builds. But belief is not proof. The interior of a spinning black hole remains contested territory at the frontier of theory, and the honest statement, the one I owe you, is that when the door is genuinely unknown, no one can promise you what is behind it. You chose the slow hole partly for this reason. Your ending, at least, is comprehensible. Now, while the tide climbs, one more comparison, because nothing teaches the scale of your destination like its small, savage cousins. And because you have seen one of those too. Before the deep voyage began, The Odysseus toward a neutron star, the middle child of stellar death. The thing that forms when the collapsing core is heavy enough to crush atoms but too light to breach the horizon. You parked at a respectful 100,000 kilometers and studied it for days, and the numbers still visit you at night. A ball 20 kilometers across, the size of a city, containing 500,000 Earths worth of mass. A surface gravity 100 billion times Earth's, so severe that the tallest mountains on the star are millimeters high, and climbing a centimeter of that terrain would cost more energy than climbing out of Earth's gravity entirely. A teaspoon of its interior outweighs a mountain range. Its crust is a crystalline lattice of crushed nuclei 100 billion times stronger than steel, and when that crust occasionally cracks, in events astronomers call starquakes, the released energy has been detected from halfway across the galaxy. And beneath the crust, the matter dissolves into states with names like nuclear pasta, sheets and tubes and gnocchi of nuclear material, arranged by the compromise between nuclear forces and unbearable pressure, the strangest material states in the known universe. Some neutron stars spin 700 times per second, their equators moving at a quarter of the speed of light, sweeping lighthouse beams of radio emission across the cosmos with a regularity that rivals atomic clocks. And when the first of these pulsing signals was discovered in 1967 by a graduate student named Jocelyn Bell, the discovery was so unnervingly precise that the team briefly labeled it LGM1, Little Green Men, before nature's explanation emerged and turned out to be, as it usually does, stranger than the aliens would have been. The neutron star matters to your story because it is the last stand. It is the most extreme object that can exist while still being an object, still made of matter, still possessing a surface, a place, a substance. Add one more shovel of mass, roughly 3 suns in total, and no force remains in the ledger of physics, not electron pressure, not neutron pressure, not the strong force itself, nothing, and the surface falls inward, and the object stops being a thing and becomes what you are inside now, a region, a geometry, an absence with a boundary. The neutron star is where matter makes its final argument. The black hole is where the argument ends. And you remember, floating in the dome with the tide beginning to pull at your ankles, what the mission's oldest physicist said on the last night before departure? A woman who had spent 60 years on these objects, who had helped photograph the first horizon, and who shook your hand with both of hers and said the thing you have carried the whole way down. She said, "We spent a century learning that the universe makes these things, and the entire time, the real discovery was hiding in the arithmetic. The discovery that there is nothing exotic in the recipe. Gravity, patience, and enough mass. That is all a black hole is. It is what everything becomes when nothing can hold it up. It is the universe's default, deferred. Every star you have ever seen is a postponement, and now with the horizon hours away and the ship falling true, let yourself imagine the roads not taken, because the mission planners offered you 3 destinations before you chose this one. And what your fall would have been at each of the others is a lesson in how utterly the same object, at different masses, becomes a different fate. The first candidate was a stellar mass black hole, a 10 solar mass remnant drifting in the spiral arm, not far cosmically speaking from home. Falling into it would have gone like this, and I will not soften it. The approach at first is identical. The same weightless serenity, the same lens sky, the same crowding of starlight into rings. Only everything is smaller. The shadow ahead of you the size of a city rather than a solar system. And the timeline compressed from months to hours. The trouble begins at a distance that sounds absurdly safe. Several thousand kilometers out, farther from the horizon than New York is from Los Angeles. The tide across your body reaches the strength of Earth's gravity. Your feet pulled toward the darkness, one full gravity harder than your head. And from there, the cube law takes the arithmetic and runs. At 2,000 kilometers, the differential is 10 gravities. The sensation of a giant gripping your ankles and your shoulders and leaning apart. And the mission physicians are blunt about this stretch of the descent. It is survivable and it is agony. At 1,000 kilometers, 80 gravities of stretch and no training, no suit, no restraint system matters anymore. Because the force is not pressing on you from outside, where engineering can fight it, It is pulling every gram of you from within, each vertebrae separating from the next. And consciousness, mercifully, is already failing. The blood unable to complete its circuit through a body that gravity is sorting by altitude. By 500 kilometers, the connective tissues fail. What continues the fall is no longer a person, but a lengthening plume of what a person was, drawn finer with every kilometer, tissue into strands, strands into cells, and the physics does not pause at any point that resembles death to acknowledge the milestone. It simply continues the stretching through every scale of structure, cells into molecules across the next 100 kilometers, molecules into atoms, and near the horizon itself, the tidal gradient reaches millions of gravities per meter, and the atoms themselves surrender their electrons, so that what crosses the 20-kilometer boundary of a stellar black hole, less than a millisecond after the last coherent heartbeat, is a needle of ionized plasma, kilometers long, thinner than a human hair, entering at a substantial fraction of the speed of light. And inside, with the center only microseconds ahead in time, the compression finishes what the stretching began. From your first twinge of discomfort to the singularity, perhaps 4 seconds. That is a stellar mass fall. 4 seconds of catastrophe at the end of an approach you spend entirely intact and entirely aware of what is coming. You declined. The second candidate was Sagittarius, a star itself, the black hole at the center of our own galaxy, and this one you turned down with genuine regret, because there is a poetry and ending inside the engine. Your whole civilization orbits the 4 million solar mass anchor that every star you have ever seen, every photon that ever touched your skin, has been circling at 500,000 kilometers per hour since before the Earth existed. Sagittarius, a star, is large enough to cross intact, its horizon gentle enough to survive, and the interior would have granted you seconds, roughly 20 of them, by the ship's clock, between crossing and center. 20 seconds is enough to see the universe gathered overhead. Enough for one long, deliberate thought, enough, perhaps, for a sentence spoken aloud into the dome. And the mission poets, there were poets on the committee, that surprised you too, argued hard for those 20 seconds, and their symbolism, the traveler dissolving into the heart of home. But 20 seconds is not hours, and you had questions that needed hours. And there was a subtler problem, a practical one, which is that the center of the galaxy is a bad neighborhood. Sagittarius, a star, is orbited at insolently close range by a swarm of stars and gas clouds, and its immediate vicinity crackles with radiation from the accretion of stray matter, faint by quasar standards, but lethal by yours, and threading a ship through the innermost light year of the galaxy, past the S-stars whipping by at thousands of kilometers per second, past the paradoxically young stars that should not be able to form there and stubbornly have, past the gas streams and the stellar corpses concentrated by 4 billion years of dynamical friction into gravity's densest parliament, was a navigation problem the planners priced at unacceptable risk. The center of the galaxy does not welcome visitors. It collects them. And the third candidate, the one that made the committee go quiet when its slide appeared, was TO in 618, or rather, the class of giant it represents. An ultra-massive black hole of tens of billions of solar masses, the largest gravitational structures in the universe, holes whose event horizons are wider than entire solar systems many times over, whose shadows could swallow the orbit of Neptune thousands of times, objects so large that falling through the horizon of one, you could have days inside, possibly a week, a whole final chapter of life conducted entirely within a black hole. Meals and sleep and experiments and grief and awe, an interior expedition, and the tided crossing so vanishingly gentle that instruments strain to detect it. Gravity's most colossal objects being, at their boundaries, the softest places in all of physics. You wanted it. Understand that you wanted it badly, but the ultramassive holes live in the cores of giant elliptical galaxies at cosmological distances, hundreds of millions to billions of light years out. And no ship, no program, no species with your lifespan reaches them. And there was something else too, something the eldest physicist said when you pressed the point, and which settled it. She said, at 40 million solar masses, you will have 4 hours. And I promise you that 4 hours inside a black hole will exceed the capacity of a human mind to spend. A week would not be more. It would only be longer. You believed her. You believe her more with every hour of this descent. One more thing from the briefings belongs to you before we return to the fall. A controversy, a live one. Because I told you that you would cross the horizon and feel nothing. And I owe you the disclosure that for a stretch of the 2010s, a significant fraction of theoretical physics was not sure that was true. The dispute is called the firewall paradox, and it erupted in 2012 from a careful analysis of the entanglement between the radiation a black hole has already emitted and the radiation it is currently emitting, an analysis which seemed to prove that the demands of quantum mechanics could not all be satisfied at once by a smooth, uneventful horizon, and that something had to give. And one of the candidate somethings was the equivalence principle itself, Einstein's founding insight, the smoothness of the crossing, with the alternative being that an infalling traveler meets not gentle emptiness at the boundary, but a seething curtain of high-energy quanta, a firewall in which ship and traveler are incinerated at the threshold rather than stretched at the center. The debate consumed the field for years, set the giants of the discipline against one another in public, and drove the burst of breakthroughs in holography and entanglement that eventually, in the view of most though not all researchers, dissolved the paradox in favor of the smooth horizon, the interior space-time emerging from the entanglement structure itself, geometry stitched from correlation, the fall as gentle as Einstein promised. Most, though not all. You crossed on the majority opinion, and it held, and you are alive inside to know it, which makes you, among your many other distinctions tonight, the first experimental result in the firewall debate, a data point no one will ever collect. The ship falls on. The shadow below has long since ceased to be a shape and become a hemisphere, a world of darkness rising to meet you. And the last landmark of the exterior universe is approaching, the innermost stable circular orbit, the final altitude at which anything can circle a black hole and persist, the inner shoreline of the accretion disk when this giant last fed. Inside that radius, orbits are not difficult. They are non-existent. Every path spirals inward, regardless of speed, and as the Odysseus crosses the line, the ship marks it with a single, soft tone, the sound the planners chose for thresholds. And you realize it is the last threshold with a name on the outside. Below this, there is only the crossing itself, and then the interior, and then the center, and the mission clock, which has counted down through so many phases of your life, now shows a single figure, the proper time remaining to the horizon. And you watch it fall through minutes the way you once watched the last minutes of ordinary days, in kitchens, in winters, on the shore of the ocean whose tides first taught your species that the sky pulls on the sea. And you had no idea, none of you had any idea how far down that lesson went. You cross. There is no wall, there is no membrane, no flash, no jolt, no sensation of any kind. The event horizon is not a place, not a surface you could touch, not a barrier of energy. It is a line drawn in the mathematics of space-time, the radius at which escape velocity passes the speed of light. And locally, at the moment of crossing, the space-time around you is as smooth and unremarkable as the space above your childhood home. You are watching the clock when it happens. The mission computer, calculating from the ship's trajectory, counts down to the crossing. 5, 4, 3, 2, 1, and then nothing. The dome is quiet. The amber lights glow. Your heart beats. You are inside a black hole and you feel completely normal. And somehow that is the most disorienting thing that has happened on this entire journey. Some part of you expected the universe to acknowledge the moment. It did not. The universe does not mark its most profound boundaries. It lets you drift across them, mid-breath, mid-thought, mid-heartbeat, and leaves you to work out afterward that everything has changed. And everything has changed. Look up. The universe is still there. And this surprises almost everyone who studies black holes for the first time. Light from outside falls in behind you without difficulty. The horizon is a one-way door, not a blindfold. And so the stars, the galaxies, the whole luminous cosmos remains visible above you, gathered into a shrinking circle of brilliant blue-shifted light. You can still see them. They can no longer see you. Every photon you emit now, every radio pulse, Every glint of your running lights, every trace of you travels inward no matter which direction it is fired. You could point the ship's transmitter straight up, straight back along the way you came, and fire a signal at the full speed of light. And that signal would curve away from the horizon and fall toward the center, like a swimmer stroking upstream in a current faster than any swimmer. That is what the horizon means from the inside. Not that the door is locked, but that every direction is down. And here you need to understand the deepest strangeness of the place you now inhabit. The thing that separates the inside of a black hole from every other environment in the universe. Outside the horizon, the singularity at the center was a location, a point in space you could point toward, approach, or in principle, steer away from. Inside the horizon, the mathematics of space-time performs a quiet inversion. The radial direction, the direction toward the center, exchanges roles with time. The singularity is no longer a place ahead of you. It is a moment ahead of you. It is not somewhere you are going. It is something that is going to happen to you, as fixed and unavoidable as next Tuesday. And steering away from it makes exactly as much sense as steering away from tomorrow. Fire your engines toward it, away from it, sideways. It does not matter. Nothing you do can prevent the arrival, because the arrival is not in your space. It is in your future. The mission physicists tried to prepare you for this idea, and you nodded along in the briefings. But floating here now, watching the far universe glitter in the shrinking window above, you finally feel the truth of it in your body. You have fallen out of the geography of the universe and into its calendar. There is a strange peace in it. Every anxiety you have ever had was, in the end, about steering, about choices, about which way to turn. Here there are no turns. The remaining path has one direction and needs nothing from you. For the first time in your life, the future is literal. You have, by the ship's clock, a little over 4 hours. That is the gift of a supermassive black hole, and it is the reason you chose this one. Had you fallen into a stellar mass black hole, a small one, the interval between horizon and center would be measured in microseconds, and long before the horizon, you would have been destroyed by the tides. And we will speak about the tides soon, because they are coming for you too, even here, even in this gentle giant. But for now you have time. 4 hours to fall through the interior of a black hole with your eyes open. Nobody has ever had this. The mission planners filled the schedule with experiments, and you run them faithfully, transmitting inward toward instruments you released earlier in the descent, timing light pulses, measuring the tidal gradient, feeling the geometry with the ship's exquisite sensors. But mostly, between the tasks, you watch. The view above you is changing in ways that no artist ever painted. The circle of the outside universe is shrinking as you fall, and it is doing something else too, something subtle and wonderful. It is speeding up. Because your time now runs slow relative to the cosmos in a ratio that grows as you descend. The universe overhead is running fast from your point of view, and getting faster. Stars in the window above are twinkling with a strange urgency. You watch a variable star that should pulse once every 11 days, brighten and dim in what feels like minutes. The universe is racing through its history while you fall gently down the well, and if the black hole were even larger, and your fall even longer, you might watch stars visibly age, galaxies visibly turn. Epochs of cosmic history flicker past in the closing eye of light above you. You are watching the future of the universe happen at a distance, and it costs you only everything. 2 hours in, you decide to conduct the experiment you were most curious about, the private one, the one that appears in no mission plan. You unstrap a small drone from the equipment bay, a sphere of instruments the size of an apple with a bright white beacon, and you release it ahead of the ship, letting it fall just slightly faster along the inward line, watching its light pull away below you into the dark. Here is what you see, and I want you to picture it exactly. The beacon does not simply recede. As the gap between you widens, the drone's light stretches and dims and reddens, its steady flash slowing like a heartbeat falling asleep. And there is a horizon below you too now, a personal one. Because in this curved place, even the light climbing from the drone back up to your eyes fights a current, and there comes a distance at which its light can no longer close the gap. The beacon flashes slower, dimmer, redder, a cold cooling in dark water, and then it simply is not there anymore. Not switched off, unreachable. The interior of a black hole is layered with these private horizons, every falling object eventually sealed away from every other, each traveler ultimately alone with the geometry. You understand now why the mission psychologists spent so long on solitude. The dark below you is not empty, you know that. Everything the black hole has ever swallowed fell along lines like yours. Somewhere below, long ago by any clock, the atoms of ancient stars passed this way, in clouds of primordial gas, and perhaps in 40 million solar masses of accumulated history. Other things too, wanderers, debris of worlds, the patient inventory of 1 billion years of feeding. All of it fell through this same silence, and none of it can ever signal to you, nor you to it. The interior of a black hole is the loneliest architecture in existence, a cathedral in which every visitor is sealed in their own pew, falling. And yet, you look up at the shrinking, racing, blue-white circle of everything, and you look down at the dark that holds every previous traveler, and you find the loneliness is not quite what you feared. The photons landing on your retina right now left the outside universe after you crossed. The cosmos is still writing to you, still delivering its light down the well, and will keep delivering it until the end. You cannot answer, but you were never able to answer the stars. No one on earth ever could. We only ever received their light and loved them without reply. Falling here, wrapped in one-way starlight, you are doing what your species has always done, at last in its purest form. 3 hours in, the ship's sensors register the first whisper of what the physicists call the gradient, and what you have privately thought of ever since the first briefing. As the reef, the tides are rising, it is time you understood exactly what is about to happen to you. And to understand it, come back with me to Earth for a moment, to the ocean you grew up beside. The moon raises tides on Earth because gravity weakens with distance. The ocean on the side of Earth facing the moon is pulled harder than the planet's center, and the center harder than the far side. And this difference in pull, this differential, stretches the whole planet gently along the line joining it to the moon. 2 bulges of water, 2 tides a day. The force is tiny. Across the 8,000-mile width of the Earth, the moon's differential pull amounts to almost nothing, a delicate kneading that moves water a few meters. Now compress the source of gravity and bring it close, and the arithmetic turns vicious. The differential pull across an object grows with the inverse cube of distance to the mass. Halve your distance and the tide grows 8-fold. Divided by 10, the tide grows 1,000-fold. Near a stellar mass black hole, this cubing runs away to catastrophe while you are still far outside the horizon. Across the 2 meters of a human body, feet toward the hole, the pull on your feet exceeds the pull on your head first by a factor that feels like hanging from a bar, then by one that feels like a rack, then by thousands of times the force any bone or ligament can bear. Your body is drawn out along the line of the fall, thinning as it stretches. Because the same geometry that pulls you long also squeezes you narrow. The sideways components of gravity all converging toward the center line. Physicists, with the gallows precision of their profession, name this process spaghettification. And they are not joking. That is the real term, printed in real textbooks. Matter falling into a small black hole is drawn into strands, and the strands into thinner strands, the way a glass blower pulls molten glass into thread, until what arrives at the horizon is a filament of atoms kilometers long and thinner than a hair. For a small black hole, this happens to a falling traveler well outside the boundary, which is why your mission planners never considered one, and why every fictional depiction of a person crossing a stellar black hole's horizon intact is physically wrong. You do not meet a small black hole. You are shredded on its approach, reduced to a luminous thread of plasma, and the thread spirals in without you, because you, as an arrangement, as a structure, as a person, ended kilometers above. Your black hole is 40 million times the mass of the sun, precisely because mass, paradoxically, is mercy. The bigger the black hole, the farther the horizon sits from the center, and the gentler the gradient at the crossing. At your horizon, the tide across your body was billions of times weaker than the tide you felt standing on Earth. That is why you are still whole, still breathing, 3 hours inside. But the center is coming, the center is always coming, and the cube law does not sleep. The reef is rising beneath you. The first hour inside the black hole, you spend learning the light. Because the interior has weather of a kind, optical weather, and no simulation rendered it correctly, the planners admitted as much before you left. The geometry down here bends light along paths so tangled that the honest answer to what will I see was always, tell us when you get there. So you tell them into the recorder, knowing the words go only inward, and this is what you say. The circle of the universe overhead is not static. It breathes. As you fall, the lensing reshuffles constantly. Star images sliding along the rim of the circle, splitting into pairs, merging, brightening in sudden caustic flares as the geometry aligns and then letting go, so that the edge of the shrinking sky glitters and runs like light on the surface of a pool. And once for a few seconds, an entire background galaxy is drawn into a thin, complete ring around the disk of the sky. A perfect circle of 100 billion suns, and then the alignment passes and the ring collapses back into a smudge of ordinary light. Below the rim, where the darkness begins, the black is not uniform. It is layered, structured by faintness itself, because light from outside that entered before you on steeper paths is still down there falling, and some of it scatters off the thin plasma. The black hole endlessly swallows, so the abyss beneath you carries a whisper of illumination, a haze of drowned starlight, the ghost light of everything the hole is currently eating. And the deeper you look, the older that infalling light is. So that in a real and literal sense, looking down inside a black hole is looking at the buried light of earlier ages of the universe, pressed into the dark like leaves into coal. You map the layers for an hour, and the recorder takes it all. And you find yourself narrating in a voice you recognize from somewhere old. And eventually you place it. It is the voice of a child explaining the tide pools to a parent. The voice of the first time you ever understood that the world would let you look at it as long as you wanted. That looking was allowed. That looking was the whole point. Meanwhile, in the other story, the one running on the outside, Mission Control is living the same hour across 11 years. This is worth seeing clearly, the two clocks side by side, because nothing else in your journey makes relativity as honest. In the hour after your crossing ship time, the stretched trickle of your final approach telemetry arrives on Earth across a decade. The signal engineers hand their consoles to their successors. The data from your last 1,000 kilometers above the horizon, 1 hour of your life, is parceled out to them in packets years apart, each one an event, each one a headline. The last photograph reconstructed pixel by pixel across administrations, and somewhere in year 6 of that decade, by their calendar, a technician on the night shift decodes the frame in which you raise your hand to the dome, the wave you gave your own ghost in the photon ring, and the image crosses the planet by morning, and a species that has burned itself down and rebuilt 100 times over stops. For one day, all of it, every feuding corner of it, to look at a picture of one of its own, waving at the edge of the deepest place there is. You do not know this happens. You cannot ever know it happens. It happens anyway, which is perhaps the purest thing that can be said about every good act in the universe. And the physicists at Mission Control, in that same decade, do something quietly heroic with your data. They complete the map of the exterior, the strong field measurements orbit by orbit, confirming the metric of the space-time around the hole to a precision astronomy had never touched. And where your telemetry ends at the horizon, they mark the boundary of the empirical, the shoreline of the measurable universe, and they inscribe on the final page of the mission's published archive a sentence you would have liked, the last line of the last report, which reads, "Beyond this radius," the traveler continues, and the science waits. Back inside in your hour, you conduct one experiment that was on no schedule, using nothing but a flashlight from the tool locker, and it teaches you more than the instruments did. You float in the center of the dark cabin, and you point the beam straight up toward the shrinking sky, toward the way you came, and you turn it on. The beam rises from the lens, bright and confident, and it does not leave the ship slower. Light never travels slower, but the geometry receives it and bends it. And through the dome you watch your own beam curve, gently, unmistakably, like a stream of water thrown upward against a wind, arcing over and inward, its light joining the fall. And you stand in the dark holding a flashlight whose beam will hit the center of the black hole before you do. You try it in every direction. Up, sideways, backward along the orbit. At every angle the beam bows inward. Every path lit up and shown to be a curve toward the same destination. And the cabin fills with faint returning glow. Your own light delivered back to you by the geometry, and you understand, holding the flashlight, that you are seeing the true shape of the place with your own eyes, the funneling of all futures drawn in the air in torchlight, and that no human being has ever performed a simpler experiment or a deeper one. Every child who has ever pointed a flashlight at the night sky was performing the control run of this experiment. The beam goes straight, the sky receives it, the light leaves forever. Yours comes back. That is the whole difference between the universe and the inside of a black hole, and it fits in one hand. The third hour inside is the quiet one, and it is the hour you will remember, if remembering is a thing the universe lets you keep. The experiments are done. The drones are gone below, sealed behind their private horizons. The tide is still a whisper, and the dome is dark except for the shrinking coin of blazing sky. And you find that your mind, with nothing left to measure, has turned to the cargo every traveler actually carries, which is everyone they have ever known. You think of the people at Mission Control, who by your clock said goodbye this morning, and by their own clocks said goodbye years ago. Time dilation has already carried you into their future. The controllers who trained you have retired. The children who drew pictures of the Odysseus for the launch broadcast have children. If you could see Earth now through some impossible telescope, you would see a world that has moved on without moving on, that still receives every year on the anniversary one more agonizingly stretched syllable of your final transmission, your voice arriving like honey poured in winter. A single word of farewell that their instruments will spend a decade completing. You knew when you volunteered that a one-way trip into deep time is a bereavement you inflict in both directions. They lost you at launch. You are losing them now, hour by hour, as the racing light overhead spends their lifetimes. And you notice what you feel about it, here in the dark, and what you feel is not what you expected. You expected grief, and grief is present. But present with it is something the mission psychologists never named. A fierce and almost unbearable tenderness for the ordinary. An understanding arriving decades late the way understanding does, that every unremarkable evening you ever lived, every kitchen conversation, every walk to the corner in the rain, was taking place on the thin, bright surface of a universe whose default condition is this: silence, darkness, gravity, and depth. People ask what the point of studying black holes is. What an object that destroys everything can possibly teach us about living. You know the answer now, and it is not in the equations. The answer is that you cannot understand what light is worth until you have fallen somewhere it cannot follow you out of. The interior of a black hole is the only vantage in existence from which the entire visible universe fits within a single circle, like a portrait in a locket, and the universe put every one of its trillion galaxies inside that locket for you, and the price of seeing it is that you can never hand the locket back. So you spend the quiet hour doing the only thing there is to do with a view like that. You memorize it. There, in the compressed and lensed disk overhead, is the whole neighborhood of your species. Somewhere in that circle, folded and refracted, nowhere undersoriated, is the Milky Way seen from outside, the spiral city of 400 billion stars where everything that ever happened to anyone happened. Somewhere in it is the sun, unresolvable, one grain among the billions, and orbiting that grain, invisible, immeasurable. The wet blue world where a fish first crawled on the mud, where trilobites flourished for 270 million years and were forgotten, where dinosaurs watched the sky for the wrong threat, where a primate picked up a bone and wondered, where Michel preached his Sunday sermons and quietly invented dark stars between them, where Schwarzschild solved the universe in an artillery trench, where a graduate student found a signal that ticked like clockwork and dared to write it down, where engineers linked telescopes across a planet to photograph the very kind of shadow you have now sailed into. All of it in the locket, all of it in the light. The photons carrying that history down to you are the last mail you will ever receive, and you read every line of it, and you understand something in that hour about the shape of every life, which is that consciousness itself has always been what you are now, A region of pattern falling through a universe it can see but not stop. Receiving light from a past it can never answer. Moving toward a future it cannot steer away from. And the fall was never the tragedy. The fall is the condition. The tragedy would have been falling with your eyes shut. Then the ship's medical system chimes, softly. The tone the physicians programmed for the beginning of the gradient, and the quiet hour is over. You have 20 minutes, and you have already decided how they will be spent, and we have already lived them together. You and I, the creaking hull, the last log entry, the voice speaking calmly into the dome, the disk of everything overhead, the note, the string, the lifting. So instead, in the time that remains before we return to that ending, let me answer the question that every single person watching this has been holding since the beginning. The question you are perhaps slightly ashamed of because it sounds like science fiction, and which deserves a straight answer precisely because it is asked by everyone from children to tenured physicists. Could the fall lead somewhere? Could a black hole be a door? Here is the honest state of human knowledge. The equations of general relativity do contain doors. The extended mathematics of the Schwarzschild solution includes a structure called an Einstein-Rosen bridge, a throat of space-time connecting two separate regions, two universes, or two distant places in one universe. And this is not fringe speculation. It was published by Einstein himself with his collaborator Nathan Rosen in 1935. The bridge is real mathematics. What it is not is traversable. The throat of the Schwarzschild bridge pinches shut faster than anything. Even light can pass through it. Every traveler who enters meets the pinch. The door exists and closes on everyone, always by geometry, not bad luck. To prop such a throat open, the equations demand a material with negative energy density, a substance that gravitationally repels, weighs less than nothing. And while quantum mechanics does permit whispers of negative energy in exotic laboratory configurations, the quantities are absurdly small, and rigorous theorems bound how much can be gathered and for how long, and every honest calculation concludes that holding open a human-sized wormhole would require negative energy in planetary quantities that the laws of quantum field theory appear to flatly forbid. So the summary you deserve is this. Doors, yes, in the mathematics. Passage, no, in the physics, so far as a century of our best minds can determine. The black hole below you is overwhelmingly likely to be exactly what it appears to be, an ending with extraordinary interior decoration. And yet the history you carried down with you counsels one final humility, because Michel was dismissed, and Chandrasekhar was mocked, and Einstein himself published proofs that the object you are inside could never form. The experts were wrong about black holes at nearly every stage, always in the same direction, always underestimating how strange the universe was willing to be. The reasonable bet is that the singularity is an end, but the universe has never once been obligated to be reasonable. And if there is one lesson written across the entire scientific history of these objects, it is that the phrase that could never happen has a shorter half-life than anyone expects. And one final gift before the tide, a small one, the kind the universe leaves in coat pockets. In the last calm minutes, the ship's spectrometer, still dutifully sampling the thin plasma the hole forever swallows, flags a signature in the infalling haze, and you read the readout twice to be sure. Water. Traces of it, ionized and ancient, molecules of water falling beside you in the dark. Water that formed in some interstellar cloud billions of years ago, that perhaps rode a comet, that perhaps rained on some world you will never know the name of, and is finishing its journey here, in your company. You think of every ocean you ever stood beside. The universe began delivering water to this place before your sun ignited, and it saved some to fall with you, and you decide, with the last unhurried thought you will ever be given, to take that personally, to accept it as company, because the cosmos is under no obligation to be companionable. And here it is anyway, raining very slowly, in the dark, all the way down. The readout scrolls on and finds carbon in the haze, in silicon and iron. The same iron that reddens human blood, the ordinary alphabet of matter falling all around you in whispers, and it settles something you had wondered about since childhood, whether the mouth of a black hole would feel alien. And the answer is the opposite. The answer is that it is made of everything familiar, The universe does not stock this place with exotic horrors. It fills it with rain and rust and starlight, the same inventory as home, only finishing differently, and you find that this, of all things, is what finally makes the place feel survivable. In the only sense that matters now, not survivable by the body. That question is closed, but survivable by the understanding. A place the mind can hold without breaking. A place that can be known and you knew it. You are knowing it right now, and no horizon in existence was ever able to stop that from happening. Above you, the locket of the sky has shrunk to the size of a coin held at arm's length, burning blue-white at its heart, ringed with the folded fire of every galaxy. And it is still shrinking, and it will go on shrinking after you are gone, closing over the drowned light like water over a stone. And you look at it the way you once looked at the last window of a train leaving a city you loved, and you do not look away. Somewhere in that coin of light, unfindable and certain, is the room where you first heard the words, black hole, and the person who said them to you, and the night sky you walked out under afterward, newly afraid of it and newly in love with it, and the whole chain of evenings that led from that one to this one, link by link, and you honor the chain the only way a falling traveler can, by finishing it awake. You check the seals on nothing. You straighten instruments that need no straightening. The small liturgies of hands that want work, and then you let the hands be still. Let us use the time you have left the way you would want it used. Let me tell you what is below you. Because the honest answer, the answer that every physicist alive would give you if you caught them in a truthful hour, is that nobody knows. And the reasons nobody knows are the most important unsolved problems in all of science. The equations you have trusted your whole descent, the equations of general relativity, which predicted the lensing you saw, the photon ring where you waved at yourself, the time dilation stretching your signals, the horizon you crossed without a bump. Every one of those predictions verified to the decimal. Those same equations, followed all the way down, predict that at the center of this black hole, the curvature of space-time rises without limit. The density of whatever carries the mass rises without limit. And at the central point itself, the equations return infinity. And infinity in physics is not an answer. It is a confession. When a theory outputs infinity, it is telling you, in the only language it has, that you have pushed it past the edge of its validity, that some deeper theory takes over where it fails. The way Newton's clean clockwork gravity fails near massive bodies and hands the problem to Einstein. At the singularity, Einstein hands the problem to someone who has not arrived yet. The trouble is that the deeper theory must merge the two great pillars of modern physics, general relativity, which owns the large and the heavy, and quantum mechanics, which owns the small and the uncertain. And after a century of effort by the most brilliant minds our species has produced, the two theories still refuse to combine. Each is tested to stupefying precision in its own domain. Together they are incompatible. And the center of a black hole is one of the only places in the universe where both must apply at once. Enormous mass, vanishing size, gravity, and the quantum in the same room with no chaperone. Some physicists believe the answer is string theory, in which the point particles of ordinary physics are tiny vibrating filaments, and the singularity is smoothed into something finite, an exotic knot of energy rather than an infinite spike. Others pursue loop quantum gravity, in which space itself is woven from discrete threads, and there is a smallest possible volume, and nothing can be compressed past it, in which case the center of your black hole holds not an infinity, but a seed, matter crushed to the very floor of existence. The Planck density, a state so extreme that one sugar cube of it would outweigh the entire observable universe. And some loop theorists suspect such a seed might even rebound in some deep future or some inaccessible elsewhere. A bounce instead of an end, and a few have wondered aloud in respectable journals whether the Big Bang that began our own universe might have been exactly such a rebound seen from the inside, whether every black hole is an egg, whether you are falling right now toward the kind of event that once hatched everything you have ever loved. These are hypotheses, not knowledge. I will not pretend to you here at the end that anyone knows. What waits at the bottom of your fall is the deepest closed door in nature, and you are about to be pressed through its keyhole. There is one more piece of physics you deserve to hear before the reef arrives, because it concerns what the universe will ultimately do with you, and it is stranger and lovelier than anything else in this story. For half a century after black holes were first taken seriously, physicists believed that they were eternal, that a black hole once formed would persist unchanged to the end of time, growing but never shrinking, taking but never giving. Then in 1974, a young Stephen Hawking, studying how quantum fields behave in the curved space-time near a horizon, found something in the mathematics that he initially refused to believe. The vacuum of empty space, quantum mechanics insists, is not empty. It seethes at the smallest scales with fleeting fluctuations of energy and near an event horizon. Those fluctuations are torn open in a way that empty space elsewhere never experiences. And the result is that the horizon glows. Faintly, almost immeasurably faintly, but truly. A black hole radiates. It has a temperature. And because it radiates, it loses energy. And because energy is mass, it loses mass. And because it loses mass, it shrinks. And because smaller black holes radiate more fiercely, the shrinking accelerates, slowly at first, over spans of time that make the age of the universe look like nothing at all, and then faster, and then at the very end, in a final flash of high-energy radiation, the black hole is gone. Nothing in the universe is permanent. Not even this. The numbers are beyond all intuition. Your 40 million solar mass black hole, left alone in an empty and ever colder universe, would take roughly 10 to the power 92 years to evaporate. A 1 followed by 92 zeros. A span so vast that if you compress the entire current age of the universe into a single second, the evaporation would still take unimaginably longer than the age of the universe measured in those compressed seconds, layered again and again. And yet the number is finite. That is the point. That is the revelation. The black hole is not a grave. It is a very slow furnace. And everything it has ever taken, every gas cloud and wandering comet, every shredded star, and one small ship called the Odysseus with one volunteer aboard, all of it will be paid back out into the universe, particle by particle, over the long dark ages at the end of time. Whether the pattern of you, the information of you, comes back out scrambled beyond recovery or secretly encoded in subtle correlations within that radiation, is the black hole information paradox, the deepest open argument in theoretical physics. A question that has consumed careers and spawned entire fields. And the emerging consensus, hard won over the last decades, is that information is not destroyed, that nothing is ever truly lost, that the universe keeps its books and everything that falls, everything, is eventually, in some transfigured form, returned. Hold that thought. Hold it now because the ship has begun, very gently, to creak. The tide has found the Odysseus. It began below the threshold of feeling. The sensors caught it first, a differential of grams between bow and stern, then kilograms. And now you feel it yourself. A faint lightness in your head, a faint heaviness in your feet, as though the ship were slowly waking up to gravity after the long weightless fall. The cube law is climbing. You have perhaps 20 minutes of comfort left, and after a lifetime of wondering, you find you know exactly how you want to spend them. You dim the cabin lights, you float to the center of the diamond dome. Above you, the universe has contracted to a disk of brilliant white-blue light, small enough now to cover with an outstretched hand, and inside that disk, distorted and compressed but present, is everything. Every galaxy, every star anyone has ever named or loved or steered a ship by. The light around its edge has looped the black hole on its way to you. So the rim of the disk is a halo of the entire sky folded over itself, and the whole shining circle is flickering with sped-up time, the universe rushing onward overhead, spending its future extravagantly while your minutes walk. You think about the strangeness of the word falling. Your species has always used it for disaster, falling ill, falling behind, fallen. And yet falling is the most natural motion in the universe, the purest, the only motion in which you feel no force at all. The motion the Earth itself performs around the sun and the sun around the galaxy. Everything falling around everything, forever. And it strikes you that your whole species has spent its existence in freefall without ever feeling afraid of that. and that what you are doing now differs from what every human being has always done, only in its destination. The creaking deepens. Standing is becoming strange, your feet noticeably heavier than your head, the tide across your body now like the pull of a strong hand at each end of you. The mission physicians walked you through the sequence with great tenderness in the final briefing, and their message, strange as it sounded then, was this: it will be fast, and the universe is merciful in exactly one way here. The gradient that ends you will accelerate so sharply in its final seconds that the distance between discomfort and unconsciousness is thin, and the distance between unconsciousness and the end is thinner. You transmit your final log entry inward to the recorder drones, knowing no one will ever retrieve it, knowing that is not the point. It never was. The universe does not require an audience to make an act meaningful, and neither you realize at last, do you? And because you are human, and because humans narrate, you speak the ending aloud to the empty dome, your voice level, your hands steady on the cold diamond, the racing light of everything overhead pouring down over your upturned face. Here is what happens now. The tide will pass from strong to overwhelming across a span of seconds. The Odysseus, built more finely than any machine in history, will be drawn long and pulled thin, its hull flowing like taffy, and you with it, and there will be a moment, one single moment, when the differential across your body crosses the threshold your structure can hold. And consciousness will end mid-thought, the way a note ends when the string is lifted. And after that, though there will be no you to witness it, the process will continue with perfect indifference. Tissue to filament, filament to molecules, molecules to atoms, atoms stripped to nuclei and electrons, and finally even the nuclei themselves. The iron from the ancient supernova, the calcium, the carbon, drawn into a single file procession of fundamental particles streaming along a line of space-time toward the center, toward the place where the equations surrender. Every atom that was you will arrive within the same sliver of time, compressed beyond every known state of matter, entering the region where general relativity fails and the unknown physics begins. And what happens there, whether an infinite point or a Planck density seed or a bounce or a door, is the question your death will pose to the universe, and the universe, for now, declines to answer. And then the tide arrives in earnest, and the story runs exactly as you spoke it. The ship stretches, sings one long structural note like a struck bell, and dissolves into light and streaming matter. You are unmade with it, swiftly, in less time than a heartbeat, mid-thought, and the thought, your last, is not fear. The physicians were right. There was no room left for fear. The thought is the disk of light overhead, the whole universe in a circle small enough to cover with a hand, pouring its history down onto you, and the very last thing the pattern called you ever does is see. Before we leave mission control and close this story, there is one more chamber in the physics to show you, the deepest one, the one where black holes stop being objects of astronomy and become clues to the nature of reality itself. Because the strangest legacy of your fall is not what the black hole did to your body. It is what thinking about falls like yours did to physics. It starts with a question that sounds almost childish. When you fell through the horizon carrying your ship, your instruments, your memories, the universe outside lost access to all of it. And physicists in the early 1970s began to worry about a specific bookkeeping problem hiding in that loss. The problem of entropy. Entropy is roughly the measure of hidden disorder, the count of ways a system's insides can be arranged without changing its outside. And the second law of thermodynamics, the most unforgiving law in science, says that the total entropy of the universe never goes down. But a black hole seemed to be a cosmic shredder for entropy. Drop a library into one, a star, a civilization, all that intricate arrangement, and the black hole settles back to being described by exactly three numbers: mass, spin, and charge, a blankness physicists summarized in the phrase, black holes have no hair. If all that hidden order simply vanished from the universe's accounts, the second law itself was bleeding. A young physicist named Jacob Bekenstein proposed the repair, and it sounded outrageous. The entropy is not gone, he argued. It is stored, and the storage register is the horizon itself, the area of the boundary you crossed. Every time a black hole swallows something, its horizon grows, and the growth in area exactly accounts for the swallowed entropy. Hawking initially set out to disprove this, and instead, in the same calculation that revealed the radiation bearing his name, confirmed it and made it precise. A black hole's entropy equals 1/4 of its horizon's area, measured in the smallest units of area the universe recognizes, tiles of the Planck scale, and by this formula, black holes are not merely entropic. They are the most entropic objects that can exist. The black hole below your dissolving ship contains more entropy than all the ordinary matter in the galaxy that hosts it, and taken together, the supermassive black holes of the universe hold essentially the entire entropy budget of the cosmos. Almost all of the disorder in existence is stored on the boundaries of these silent objects. But hiding inside Bekenstein's repair was a bomb, and it took the field decades to hear it ticking. The entropy of every ordinary thing grows with its volume, with how much room its insides have. Black hole entropy grows with area, with the size of its surface. And if the maximum information a region of space can contain is set by its boundary rather than its volume, then in some deep sense the three-dimensional interior is not fundamental. The full description of everything inside a region, this is the claim, can be written on its surface. The way a hologram encodes a three-dimensional image on a two-dimensional film, and this idea proposed by Gerard T. Hooft and Leonard Susskind, and now called the holographic principle, stopped being philosophy in 1997 when a young theorist named Juan Maldacena constructed an explicit mathematical universe in which it is exactly true. A space-time with gravity whose complete physics is perfectly mirrored by a theory without gravity living on its boundary. Every event in the interior encoded, with nothing lost, in the mathematics of the surface. Maldacena's paper became the most cited in the history of theoretical physics, and its message, still being unpacked by a generation of researchers, is that space itself, the three-dimensional room you have lived your whole life inside, may be an emergent phenomenon, woven out of something more fundamental, and the loom appears to be quantum entanglement, the ghostly correlations between particles, stitched together at such density that geometry, distance, interior, all of it condenses out of pure information the way temperature condenses out of the motion of molecules. Which returns us finally to you and to the question mission control will spend the next century arguing about, the question of whether you were destroyed at all. The information paradox, the argument over whether what falls into a black hole is erased when the whole eventually evaporates, is where all these threads knot together, and the fight over it has been the engine of fundamental physics for 50 years. Hawking maintained for decades that erasure is real, that black holes break the deepest rule of quantum mechanics, the rule that information can be scrambled but never destroyed. Susskind and others fought him inch by inch, in books and conferences and calculations, insisting that the universe keeps its ledger, and slowly through the holographic mathematics, through decades of accumulating theory, the field converged, and Hawking himself conceded in 2004, paying off a famous bet with an encyclopedia. A joke with a point. Because an encyclopedia is a thing from which information can always with effort be recovered. The current best understanding, refined through a burst of breakthrough calculations in recent years, is that the radiation leaking from a black hole is not the featureless static it appears to be. It is subtly, fantastically encrypted, correlations threaded through the outgoing particles, invisible to any realistic measurement but present in the mathematics, carry the complete record, and a mind with the patience of eternity and the computing power of a universe could, in principle, collect every particle your black hole will ever emit across its 10 to the 92 years of evaporation, and from that impossible archive reconstruct everything: the ship, the instruments, the drone with its fading beacon, the traveler in the dome with an upturned face, the last thought mid-flight. Not resurrect, reconstruct is a mathematician's word, and eternity is a long address for a promise. But here's what the physics, taken at its word, actually says about you now. It says the universe never deletes. It says the boundary you crossed is not a shredder, but a safe, the most secure archive in existence, holding its contents in a format written on the fabric of space-time itself, and paying them back out, syllable by scrambled syllable, over spans of time that reduce all of history to a rounding error, and that every particle that was ever you is scheduled on the universe's own unimaginable calendar for release. The fall, it turns out, was a deposit. And when the last black holes finish their evaporation in the deepest imaginable future, in the epoch physicists call the degenerate era, when the stars are ash, the galaxies dispersed, the protons themselves perhaps long decayed, the final entries in the universe's ledger will be the radiation of the evaporated holes. Thin, cold, stretched across the dark, carrying in their correlations the encrypted history of everything that ever fell. Every star, every world, every traveler. The complete works of a universe published at last to no audience in an edition of one, and complete. Now pull back, rise impossibly back up through the horizon, back into the universe of stars and clocks and radio signals, and stand for a while in mission control, decades after launch. Because the story is not finished, and the way it continues is one of the most extraordinary truths in all of physics. On Earth, you never died. Understand this exactly, not as poetry, as relativity. In the reference frame of the outside universe, your crossing never occurred and never will. The last signals of the Odysseus, stretched and reddened by the climb out of the well, arrived slower and slower, each pulse taking longer than the last. Your final transmitted image thinning across their years, and in every telescope that watches, you remain there still. A faint, reddening ghost at the edge of the shadow, asymptotically approaching a boundary you never touch. The mathematics is unambiguous. An outside observer assigns no finite time to your crossing, and so, in the only history the outside universe can ever record, you are eternally mid-fall, eternally arriving, a permanent figure suspended in the last layer of light you were ever able to send. Somewhere in the data archives of Earth, there is a frame, the final resolvable frame, of your face turned upward in the dome, and that frame is not a picture of the past. In the strict accounting of relativity, it is a picture of an ongoing present, the version of events belonging to everyone who stayed home. Physics does not choose between their story and yours. Both are woven into the same space-time, and the fact that the universe can contain both, an ending that happened and an ending that never comes, without contradiction, is perhaps the deepest thing your journey ever demonstrated. And in the meantime, the science your descent produced reshaped human knowledge. The data stream from your fall, the tidal measurements, the light curves, the timing of your slowing signals, tested Einstein's equations deeper into the strong field than any experiment in history, and they held, and where your telemetry finally faded, theory took the baton, exactly as it did in the real history of this science. Which you should know, because everything in your story stands on it. Real astronomers spent real decades tracking stars that whip around the invisible center of our galaxy. And one of those stars, called S2, swings within 17 light hours of something dark at over 7,000 kilometers per second. And from its orbit, two teams led by Reinhard Genzel and André Ghez weighed the darkness at 4 million suns and shared a Nobel Prize for proving what it must be. Real physicists spent real careers building detectors of such absurd sensitivity that in 2015 they measured a passing gravitational wave that stretched their 4-kilometer instruments by less than 1,000th of the width of a proton, the ringing of space-time itself from two black holes that collided over 1 billion years ago. Each detection since then another voice in a growing chorus, black holes colliding all across the universe, their mergers shaking the fabric of everything. And we can hear it now. We have ears for it. Your species learned to hear gravity within the lifetime of people watching this. And real engineers linked radio telescopes across the face of the Earth into a single planet-sized instrument, and in 2019 showed humanity the first photograph of a black hole, the ring of fire around the shadow of the monster at the heart of the galaxy, M87, 6.5 billion solar masses caught glowing around in absence. And 3 years later, they photographed our own. Sagittarius, a star, the quiet giant at the center of the Milky Way. The actual dark heart your actual galaxy actually orbits. You have seen these photographs. Nearly everyone alive has. What almost no one pauses to feel is that in those images, our whole species did, in a small way, what you did in this story. We approached the edge of the knowable and we looked in. So what should you carry out of the fall, back into your bedroom, your commute, your 3 a.m. kitchen, wherever it is you have been listening from all this time? Carry the scale. There are hundreds of millions of black holes in this galaxy alone, and a supermassive one at the center of essentially every great galaxy in the sky, which means the universe is not decorated with these objects. It is organized around them, whole cities of stars arranged around darkness, including the city you live in. Carry the humility. At the center of every one of those objects sits the same closed door, the same singularity where our two best descriptions of reality meet and fail. And the next Einstein, the one who opens that door, is quite possibly alive right now. Maybe unborn. Maybe a child somewhere tonight looking at a phone screen glowing with a video about black holes. And that is not a sentimental flourish. That is simply how it has always happened. The answer always begins as a person who could not stop wondering. Carry the mercy of deep time. Even the black hole is not forever. The universe's most absolute prison slowly radiates itself away, and everything it ever held is returned, transformed, over spans of time that dwarf all history. And if the growing consensus of physics is right, not one bit of information, not one particle story, is ever finally deleted from the universe. The cosmos keeps everything. It merely rewrites the format. And carry this last thing, the thing the whole fall was secretly about. Every fear you have ever had about endings assumes that an ending is a wall. But you have now seen from the inside that the most final boundary in all of nature is not a wall. It is a smooth stretch of ordinary space-time that you cross without feeling, mid-breath, mid-thought, and what lies beyond it is not emptiness, but a region where the universe simply knows something we do not yet know. Perhaps all horizons are like that. The universe, it turns out, is under no obligation to make its endings feel like endings. If this journey held you, here is what to do, and it takes 10 seconds. Subscribe so the next descent leaves with you aboard. Like the video so the algorithm lifts it to the next traveler. And in the comments alongside the city and the hour you are watching from, leave one more thing, the question about the universe that you would ride a one-way ship to have answered. I read every single one, and the best question in the comments becomes a future video, so choose well. The stars are still up there, still pouring their unanswerable light down every well in the universe, patient as ever. Somewhere tonight, 40 million suns worth of silence is bending the sky into a ring. And now you know exactly what it would be like to fall in. Sleep well.